Okay, YouTube, in this second video of my module on logarithms, what we're going to be looking at is evaluating logarithmic expressions. And so in our last video, what we had confronted is when we have something that is in logarithmic form, we say this log, which would have a base, and we'll call this base b, and we said of y is equal to x. We say that this logarithmic form really is just another way of writing the exponent on an exponential thing. And if we want to rewrite this into exponential notation, then we would say that b to the power of our x here, okay, gives us y. And so looking at both of these side by side, you can see that x really is an exponent, and so that would mean that our logarithm is an exponent. It's just another way of writing our exponent. What we're going to be doing is using this rewriting technique in order to help us more easily evaluate logarithms. So here's my number one suggestion if you're going to be evaluating logarithms. So let's get some text going here. If you are trying to evaluate a logarithm, okay, then first try rewriting the logarithmic expression in exponential form. So here's what I want to show you. Essentially, because a logarithm is just another way of writing an exponent, and the exponent's what we're trying to find here, then looking at some expressions like this, log base b of 1, and I know that it already gives us the answer as 0 here, but you can see that if you were to try to find a value for log base b of 1, in other words, I'm saying that I don't know what this equals, then trying to rewrite this in exponential notation would be the best thing we could do, because we could say, well, then really b to the what power equals 1, and I could think of only one number that would do this, and that would be 0 here. And so one thing that I do want to point out in terms of rewriting this is it's very helpful, but also that we should start to get used to the fact that the logarithm of 1 will always be 0, because that's the only thing we could raise the base to a power of to get 1. You'd have to raise it to the power of 0. Okay. So looking at this next property here, we say log base b of b is 1. Let's just recognize that this must be the truth, because as we rewrite this exponentially, or in exponential form, we would say that our base then is b to the power of what? Well, b to the power of 1 equals b. And so it's always the case that b to the power of 1 is going to be itself, and so anytime we take log base b of b, as long as those are the same numbers there, then we should get 1 for an answer. So in terms of looking at these down here, let's go ahead and take a look at these where we don't have a value on the other side of the equal sign and we want to evaluate them. So when we look at these logarithms, let's go ahead and start with this. Really what we're asking is, hey, what could we take a base of 4 to the power of in order to get 64? So one thing we could do is kind of feel around with this. We say 4 squared. Well, 4 squared is 16. 4 to the third. Well, 16 times 4 is 64. So really, we could already say that I know that this is going to be a 3. But let's say that I'm not that certain. Well, for right now, here's what we're going to do. We're just going to take this logarithmic form thing, and we're going to rewrite it into exponential form. So remember, exponential notation, something to the power of something equals something. And what we're saying here is that our base on both of these expressions is 4. And we're saying that 4 to the power of we don't know turns into 64. And so really now this becomes a guessing game, but it's the same guessing game we were playing up here, but a little bit easier to see that, hey, you know what? Then 3 is this exponent that we're looking for here. So up here we're just going to write equals 3, and that would be the value of our logarithm, but in other words, it would be the value of our exponent. So taking a look at this next problem here, it's the interesting thing about this one is we took 5 to the power of something and got something that was less than what we started with. So here's what I'm going to tell you with a suggestion here. If you have a decimal, okay, we're going to rewrite the decimal as a fraction. And so the way we're going to do this is actually to read it. Know that when you read this, we refer to this as 2/10. So as we write 2/10 as a decimal here, okay, we could also write log base 5, I suppose, of 2/10. And I suppose that the other thing I want you to see here is, of course, that that simplifies. So when we look at this expression here, this is going to be a little bit easier to deal with, because what we're trying to find out is, hey, you know, what could I take 5 to the power of to get 1 over 5? Well, we're saying 5 to the power of, we don't know, turns into 1 over 5. Well, what is it that we could take 5 to the power of that doesn't change the fact that it's 5, but also reciprocates it? What we're going to say here is that this must be a negative exponent. Okay. So remember our property of negative exponents. We would say that if we had x to the a, it'd be x to the a, but if we had x to the negative a, okay, that's the same thing as 1 over x to the positive a here. And so with this right here, we say, what can I take 5 to the power of to get 1 over 5 to the positive 1? Well, it must have been 5 to the negative 1. And so we would say that our solution here, or our value of this logarithm, is negative 1. But also because when we rewrite it this way, we say 5 to the negative 1 power, we get 1 over 5 to the positive 1 power. So negative 1 is our logarithmic value here. Now looking at this next expression, this one's interesting because it has a fraction also, but it's got a fraction in the base. So rewriting this exponentially, let's go ahead and start by scribbling this out here. Something to the power of something equals something. And our base here looks like the base is 1/5. And it looks like 1/5 to the power of what? Well, that's what we're trying to find out here, but turn into the value of 125 here. So the question is, okay, well now, what could we take 1/5 to the power of to get 125? Well, if you recognize that 5 to the third power is 125, then what we would need to do is get 5 to the third power, but also the reciprocal of this. And so what we're going to do is we're going to say that this right here must be a negative to reciprocate it. And it would have to be 3 because 5 to the power of 3 gives us 125 here. So we would say that the value of this logarithm here is negative 3, but only because, and as I write this out here, we say 1/5 to the negative 3, that would be the same thing as 5 over 1 to the positive 3, but that gives us 125 here. And so for our last and final expression here, we say log base 36 of 6. Now this is a unique case where if we rewrite this, we say, okay, here's my logarithmic thing. What I want to know is 36 to what power turns into 6. Okay, there's our circular relationship there. We'd say, what can I take 36 to the power to get 6? Well, what I want to tell you is that what has happened here is that we've taken a square root in order for this to happen. It's just that how do we write the square root of 36 as an exponent? So let's go ahead and review a little bit here when we talk about radical notation versus rational exponent notation. So when we deal with radicals, okay, often we write them as some, I suppose I'll call this x to the a power but the bth root. And you know what, actually now that I think about it, I'm more inclined to say that this is to the mth power and the nth root because we often talk about nth roots. But we'd say in radical notation it would look like this, as a rational exponent. And remember that a rational exponent is just an exponent, it's a fraction, it's a ratio. We would say that the very same thing, these are the same meaning, would be written this way. We would say x to the m, let's see if I can get this better here, m over n power. So we're going to say that m, just to be clear on this, is the power that we were raising this base or the radicand to, and then we would say that the n represents the type of root that we are taking. And so for instance here, if we were to say the square root of 36, you know, how would we, let me write it down here, we'd say an example, would be the square root of 36. How could we write the square root of 36 as a rational exponent? Well, we would say that first of all it would be 36 to the power of something over something. But because I want to ask what is our power here for our numerator value in our ratio, then I would say that this is really 36 to the first power. So we'd say 1. And we would say, well, what root were we taking? Well, we were taking a square root, but in reality, that really has an index of 2. So we could say that the square root of 36 is really the same thing as 36 to the 1/2 power. And so looking at this here, we could say that really then what we're looking at is a situation where we could say, well, 36 to the 1/2 is equal to 6. And this is a pretty common thing with square roots, but we'd say the value of our logarithm then has to be equal to 1/2. That had to be our exponent there. Cheers.